So good morning or good afternoon, everyone, and welcome to the RFF-CMCC-NAVIGATE webinar. My name is Massimo Tavoni. I'm the director of the RFF-CMCC European Institute on Economics and the Environment and a professor here in Milan. And I'm very pleased today to host this webinar because it's a very important topic and we have two great speakers. We're going to discuss about meeting well below 2-degree targets and what that means for jobs. I think there's never been a time where job creation and the importance of jobs is more important after what we've seen in the recent months, and given the long-term objectives of decarbonization that Europe and other places in the world that's set forth. And this seminar is going to discuss both topics. And we have two great speakers, Johannes Emmerling and Vrontisi. I will introduce them in a second as we go. Just a few words from myself, and then I will leave you to the speakers to introduce the Institute and some background information. The RFF-CMCC European Institute is a partnership, is a transatlantic partnership between CMCC, which is the Italian Research Institute on Climate Change, and RFF, Resources for the Future, which is, as many of you know, an long-standing institutions in environmental economics based in Washington, D.C. And these two institutes came together and created the European Institute now 2 years ago in the making. And this is a transatlantic partnership, and indeed the seminar at 3 p.m. today is also meant to try to bring together the two sides of the Atlantic and discuss key elements of the Green New Deal or the transitions, which is related to employment. Now, this webinar is also sponsored, and we should acknowledge the sponsorship and the collaboration and partnership with NAVIGATE. NAVIGATE is a European funded project by the European Horizon 2020 program, framework program. It is a project that started about a year ago, brings together different partners from Europe and also outside Europe, Brazil and China. And it has a focus on model development, both on the systems, which has been the traditional focus on integrated assessment models, but also much more so on the people side. And I think we're going to talk about people today, so I think this is relevant for our talk today as well. The focus of this project on inequality and impacts and co-benefits and link with other dimensions of sustainable development, which are not just environmental, but also social. You can search online the website and of the project, which is sponsoring this webinar and others. Actually, this is the second one. Now we're going to have a Q&A session. So how is it going to work? We're going to have two talks. And after, we're going to have a Q&A session. To participate in the Q&A sessions, just type the questions tab. Please, if you can, also write your name and your affiliation, so that would make it easier for me to redirect questions to the speakers. And we're going to do it just after the talk. So we're going to have an half-an-hour talk by Johannes, and then another 10-15 minutes talk by Zoe. And then we're going to open it up for the last 15 minutes of the hour for Q&A. Now the webinar will be recorded and uploaded on the CMCC YouTube channel. If you have any questions, you can write at the email that you see here. So without further ado, I would now turn to our main speaker of today. I'm very pleased, of course, to introduce Johannes Emmerling, who is a senior scientist at the RFF-CMCC Institute. He's also one of the heads of the integrated assessment modeling practice and team at the Institute. Has been a long-standing researcher in our institute, and has a lot of expertise, and one of the few people who can actually manage very well theory, empirics, and modeling at the same time. So I would leave the floor to you, Johannes, and you have 25 minutes, about 25 minutes for presentation, and I'll come back for the other speaker afterwards. Thanks for listening.
Okay, yes, thanks a lot, Massimo, for the introduction, and also a welcome from myself to all the participants. And yes, so today, as Max was saying, the topic is basically employment or job impacts in the energy system. So the title of this paper that we worked on is Meeting Well Below 2-Degree Target would increase energy sector jobs. So that's kind of a spoiler already what we find in the analysis. But yeah, I will kind of go through the whole analysis and discuss a bit the issues around it. Now, first, to start with, I want to mention that this is joint work with a few colleagues, notably Sandeep and Hisham, who are at the University of British Columbia in Vancouver, Laurent Drouet, my colleague at EIEE, and also Jessica Jewell from Chalmers University. And so let's maybe briefly start with the outline of today's, the next, let's say, 25 minutes of talk. First, I will discuss two motivations for this kind of research that we've been doing. And then I have basically two parts of this lecture. One will be on the data collection efforts that we have been doing on assessing today's direct energy jobs. So this is really like an effort that especially Sandeep, who as part of his thesis, has been working on, and which has been a necessary input to the further analysis with policy implications. The second part of the talk is then by taking this kind of data that we've been collecting and implementing them in an integrated assessment model, looking at different scenarios, including a 2-degree target scenario. We want to see what happens to energy system jobs at different levels of energy technologies, different types of jobs, and of course across regions and over time. And we will basically look into basically what are the implications. So these are the three main topics of this talk. Just to start with, I think there are basically two main motivations for this, for the focus on employment effects of energy system changes. One is a more like an ethical or justice-based, which has also been kind of formalized in this idea of the just transition, that climate policies should also take into account workers and employment effects from a justice point of view. And this has been over the last 10-20 years been endorsed by the ILO, by the UNFCCC, and especially also at COP24 in Katowice, it has been formally declared that this is kind of a major goal also of climate policies to consider this effect. Yeah, so the basic question is basically what happens to all these jobs that we see in for instance, coal or oil extraction and power generation, and when we transition to, let's say, renewables and other kind of carbon-free or carbon-less intensive energy forms. And it also has a very, let's say, people dimension, as Max was saying, that of course it affects a lot of people. Here you see actually my co-author Sandeep, who this is from a book of his, where he looked at because he looked at detail in the coal industry in India, and he interviewed a lot of people, of course. And the question there always was like, well, how can I make a living while at the same time maybe the coal industry is going to be phased out because of different reasons. One major one being climate policies. There's a second argument for this kind of research besides the justice one, which is a more political one. Here maybe just an example that, well, it is important to also discuss about this topic and to take into account in political discussions. For instance, here the 2016 US presidential elections, Hillary Clinton was saying, well, she's proposing a solution by climate policies to kind of a transition for coal miners. Which then later she regretted as her biggest mistake in this campaign, whereas the winning candidate, Donald Trump, had a different approach. And he also mentioned this precisely during the campaign, many reasons. So the point is, it's also very important to know clearly about what is happening there and to communicate it well in order in the political realm. So these are, I think, the two main reasons for this kind of research and why it is important. Now, let's move into the second part, which is basically the data collection exercise, which Sandeep, as I mentioned, spent, I think, over 1.5 years to get data at a very detailed level of energy jobs across countries, many different technologies, different types of jobs. And it turns out it's quite difficult to obtain this data because they have very different types of data and different sources and different aspects to it. So basically, he has been looking at a lot of like company reports of different types, coal, oil, but also renewables, a lot of some international organizations, trade unions, research institutions, reports, statistical offices, but also personal communications to compile this kind of data set, which has more than 50 countries and a lot of detail on jobs data of the energy sector. And what basically after these 1.5 years of work, what we come up with is a database that contains data of how much jobs and employment is embedded in different energy technologies for 11 technologies, for 5 different categories of jobs, and mostly at the country level. So it's more than 50 countries. And here you can see on the left the map of the coverage. So you see it's not, of course, the full coverage because it's not easy to get for all technologies, for all countries, this data, but it's still fairly wide. And in total, we estimate that we cover around 83% of total energy jobs. And then basically, this was basically the first step. And here, maybe one thing to mention is that we focus on direct jobs. That is, we focus on jobs that are really related to energy extraction, energy consumption, or energy power generation, especially in the electricity sector, that are directly related to the production of energy. So what we don't include here is indirect jobs. So indirect jobs are like further down the value chain or further up the value chain. What kind of are the inputs that are used, let's say, including concrete or steel for let's say a coal-fired power plant, which we don't consider here. We could discuss this maybe later why not, but we really want to focus on the direct job impact. We also don't include induced jobs, which has also been discussed. This would be jobs that is, for instance, including a restaurant next to a coal mine, which of course kind of lives on the coal in that region, but it is kind of induced by the job, so it's not really related to that energy. Now, in brief, the reason why we don't include this job is that we think, well, from an economic general equilibrium perspective, in case, let's say, this coal mine were to close, these jobs would maybe go somewhere, but the money spent, etc., from a simple general equilibrium framework would not like disappear. They would just reallocate it, prices would change, etc. But it's hard to say what happened to these jobs, apart from measuring them being very difficult. There's a fourth category, informal jobs, which includes some of the workers that Sandeep has been working on, which we also don't consider here, yeah, because of also lack of data, and again, they're similar to induced jobs, basically. Okay, so basically what we did, we wanted to collect a country level data set of 11 energy technologies, as we call them. They're not technically all technologies, but let's, for the sake of simplicity, call them technologies, 5 categories and countries, and we then compute the total jobs of the energy system or of the whole energy generation for each country and at the global level. And we do this by combining simply these kind of job values per unit of electricity produced, of ton of oil extracted, etc., all the units that we have. And here we take all the kind of official international organization statistics to combine it to a comparable, consistent, and complete data set across countries of energy system jobs. So that's kind of our goal, to have something that can really be compared and is complete in the sense of measuring this kind of employment in the energy system, in the energy sector. And then we do, of course, some data analysis and some visualization of the results. And actually, in preparing this webinar, I got some comments already, one including that, well, it would be interesting to see some regional detail. And maybe here just to show how the results can look like, for instance, focusing on 3 countries. So here you see basically the jobs intensity, so how many jobs per energy consumed across countries, so it varies quite a bit. And we focus here on China, where you see that coal is kind of with over 6 million workers, the biggest sector in terms of fuels. We can look at the USA, which has actually much more balanced mix in terms of energy jobs. So we have coal, with over 100,000 workers still, but we have also high shares of oil, but also nowadays already almost 300,000 in solar, for instance, in yellow here. Or we can look at even like single countries. Here, the case for Poland, which is known to have a huge sector in coal, where basically coal is really determining the labor force in the energy sector. So this is basically all today's energy jobs based on this framework. But when over the last years of this, the last year of this project, our main question was always at the end, and the starting analysis for the second part on what happens to jobs in the future under climate change and climate policies was how many total energy jobs are there actually today. So that's kind of was, let's say, the main question that me and Sandeep and the others we were discussing since a year and a half. And it turns out it's a simple question, but the answer, we were surprised to not found easy answers. You see a lot of regional studies on the EU, for instance. You see country level studies, sectoral analysis, a study saying, well, South Africa, 120,000 people working in coal, etc. But it's very always selective, so you don't have a full picture of the global and full energy system perspective. You have this last year, IRENA had this, actually it's an annual publication, estimate on that there are around 10.3 million of jobs in only renewables, but they include also indirect jobs, and so it's not always clear how they cannot really be compared to many other estimates. There's one other source, which is this paper, or it's actually a book by Dominic and others, which is going back to a study that was kind of started by Greenpeace actually. So I think that's interesting that it had this kind of NGO-driven interest in this topic, and they do an analysis at the global level, coming up with numbers, which is great and which we wanted to use originally, and some of them we do actually use, but it's mostly focused on OECD countries, and just the regional data. They also acknowledge it's not easy to get country level data, especially for non-OECD countries, which is of course important when we want to look at the global level. So basically, we had this kind of questions. If we wanted to start the analysis first, in order to see what happens to jobs with climate change and climate policies, we first need to know how many total energy jobs there are today, and we couldn't get this number. And after like half a year after the analysis of Sandeep of all the collection was done, and then doing a lot of processing of the data, we got this final output, and we were very happy to get this number of, as you can see, around 17 million jobs. So that was just after like 2 years all in total. Finally, we had a number of total jobs based on a consistent, comparable, and complete data set. Now, maybe on a side mark, this is not exactly a black hole, but as a researcher, I have to say, this was the moment I most felt a bit related to that, because no one knew what that number was, and we didn't calibrate anything. We just could really account for single jobs and technologies and countries. And so this was the most close we came to this picture video, which you have probably seen. Okay, so we had basically the historical jobs, or the jobs as of today, and maybe just to visualize them a bit better, and we spent quite some time on that. Here you can see basically all the energy system jobs as of today. So here it's written 2020 across, and you can see, maybe quickly walk you through how we define the system boundaries, technologies, and countries. So you see on the top you have 11 technologies: coal, gas, oil, and renewables, and everything else. And then we have 5 categories. So we have construction. This is construction of power plants. Extraction, which is basically oil, coal, and gas. We also include nuclear, because we also have the fuel cycle. We have manufacturing. This is especially for renewables, so the manufacturing of, let's say, PV cells or wind turbines and others. We have operation and maintenance of existing power plants, and we have refinery for oil and biofuels. Now, a lot of these cells are empty, and this is by construction, because of course, let's say refinery you only have for oil and biofuels. extraction you only have for fossils plus nuclear. So it makes sense, and this is kind of the 5 by 11 matrix of jobs that we have. And if you look at the jobs, so you see the numbers, these are the total jobs today, which are clearly dominated by coal. In total, coal extraction with around 6.9 million jobs, followed by oil, 1.5 million, and also coal power plant operation maintenance. So these are the big chunks, but you also have already, as you can see, solar PV, 1.2 million in construction, and 1.5 million in manufacturing. And you also see quite some, I think, interesting regional patterns. For instance, in coal, of course, extraction and operation maintenance is dominated by China, which is the red color, whereas in construction, actually, in yellow you see India, which basically is responsible for half of the construction jobs in coal-fired power plants, because China has now lowered by quite a lot the construction. You see China is very big in nuclear, with around 2/3 of nuclear construction jobs. So you see there's some interesting pattern, like offshore wind, for instance, is almost exclusively in Europe, with US and China. You have Brazil, which has large shares in biofuels. So there's quite some patterns. You have the Middle East, which is mainly present in gas and oil. So there's a regional story here. There's a large regional differences, but there's also a sectoral and even a type of job difference in terms of when is construction occurring and when there's just the operation of existing power plants. Okay, so this was basically the first part of the work, which was constructing this data set and computing the number of jobs at a very detailed country, technology, and type level. Now, with this data set, basically we went to a model which would give us scenarios of how the energy system could or would evolve if, let's say, we were to follow a 1.5 degree compatible scenario. And we use these models to project, of course, the energy mix, and then therefore afterwards we will be able to compute the jobs with and without these policies. And for this we use the IEEE model, which is called which we kind of develop at the European Institute on Economics and Environment, and which basically is optimal growth model with like 17 regions linked to hard linked to an energy system model, and includes also land use. But here, of course, we focus on the energy system model. So that's really what we're interested in. So we have 17 regions, which cover most big countries plus the continents, I think, in a reasonable fashion. And we have a production function of energy, which you see on the top right, which basically includes something like 18 power and non-electric energy technologies with which we can produce energy and afterwards output. And we consider some scenarios. The first one is we use the so-called shared socio-economic pathways, which is a scenario framework developed for the IPCC, which has basically 5 main socio-economic pathways, SSP 1 to 5, which are kind of possible futures of development of GDP, population, inequality, education, which provide a consistent framework of all these variables, how they could evolve. And they, of course, they span quite a range, because we don't know how it's going to evolve in detail, but so we can use this to also assess the uncertainty range or what is possible in terms of outcomes with different scenarios. The second set of scenarios we use is kind of 2 different policy options. One being a simple reference scenario, which basically assumes, okay, we have the NDCs now, countries have committed, they are being implemented currently, but after 2030, they will just continue like this, and there's no further strengthening of climate policies, like the Paris Agreement aims for. Whereas in the second case, the WB2C, or well below 2 degree scenario, we assume that after 2030s, there's going to be an agreement leading to a carbon price such that actually we will stay below 2 degrees very likely, or even have a 50% chance of staying below 1.5 degrees by the end of the century, which results basically in full decarbonization of the economy by around 2060. Here you can see the detail. So the question is now, typically from what we get from this model is we look at the energy mix, electricity mix. We see that, well, electricity mix is basically fully decarbonized pretty soon, whereas at primary energy level it's more difficult because transportation takes longer, buildings, etc. And these are the typical results we look into. But of course, here we are interested in the job implications. So by running these scenarios, we run three SSPs, SSP 1 to 3, and 2 policies. That's why you can see here in total the total jobs in the different scenarios. On the very left, you have these around 17.5 million jobs that we just found for today, and you can see briefly the shares dominated by 6 to 8 million in coal, or 8 million in fossils. Also here on the bottom, you see that it's mostly extraction. So coal extraction is really the big job driver here. And then we have these writer panels where you see for different SSPs on the x-axis and policies, first the reference and then the 2 degree case, how these jobs look in 2050. We focus on 2050 here because it's kind of a middle ground between now and, let's say, the end of the century, where the target of 1.5 degrees is to be met. Where, of course, in the longer term, there are much more uncertainties, and we care really about the more near-term horizon. And as you can see, for instance, on the top graph, is that, well, in the well below 2 degree scenarios, you have a huge increase in the yellow, which is solar PV, and also the orange, which is onshore wind, electricity generation, much reduction in coal in black, and somewhat in gas, and well, several other changes. And overall, looking at the numbers, you see that overall there's a slight
5-minute sign.
Okay, that there's a slight increase in jobs across different SSPs. It's different, but overall, comparing well below 2 degrees and reference, there seems to be an increase by around 5 to 10 million in total jobs. And yeah, so this is the main macro outcome of these jobs. We can also look at it of how it changes over time, and here we compare basically 3 main indices that have been typically used. We know that the energy has to decarbonize. This is typically measured by the carbon intensity, which decreases to almost 0 by the end of by 2050. You basically have to fully decarbonize energy generation. Energy intensity decreases also, so we are using less energy per dollar of GDP, but it is much more difficult to obtain, and here the decreases, as you can see, are lower. And we can also add something like a jobs intensity, basically how much jobs do we need for creating one petajoule of energy. This is primary energy, just to mention. 1 petajoule, it's about the size of Novate here, the village I live in, 13,000 people. You need around 30 to 40 people for providing this primary energy at that level. And you see this value is actually, it's decreasing slightly over time because of fuel shifting and some improvement in efficiency, but the decrease is much lower. And in the dashed lines, which show the 2 degree scenario, you see this spike, especially when renewables are really installed in large quantities, leading to this increase in jobs intensity. Another important point I want to make is that we have this, so solar and wind are important, as you saw from the previous graphs. And as we have different technologies, different options, one is manufacturing. So where are these wind turbines and PV modules manufactured? And here, the problem is it doesn't matter, we cannot assign it to the country where it's installed, because they're typically manufactured in countries like today it's mostly China. So we didn't want to say they are going to be produced in the country where they're going to be installed, because that's not what happened historically. So we created this idea of a global pool, which you can see here, the numbers, which is basically all the manufacturing in renewables. And you see in the well below 2 degree scenario, it grows to over 10 million, for instance, in SSP1. So this is basically the jobs that are kind of going to be created for manufacturing solar and wind equipment. And here the global pool is basically, we assume that what today is installed, for instance, what is existing capacity for producing PV modules, etc., will be used in that country, but everything else is up for grabs. And basically depends on industrial policy, trade policies, etc., where they're going to be installed, subsidies. So we don't count them to any region. And this is really an important and large number. There are also regional differences, but the important note here is, I think, that these manufacturing jobs in renewables can be huge. And there, of course, the location depends on many other factors. So, and we don't take them into account here because we don't want to assume anything about where this equipment is manufactured. And just maybe to almost come to the conclusion. So if you look on how this picture changes from 2020, where you see here this graph, in 2050, you see this kind of, in the reference scenario, oil going cold and oil going down, renewables, solar and wind increasing, and you have this global pool, which is here denoted in black, of already 1 million new jobs, even in the reference case, which in the 2.5 degree scenario increases to, we have 5.6 million in solar PV, even CSP jobs, and another 2.3 million in wind equipment manufacturing. And these are really huge numbers, and we don't assign them, but we leave it as a global pool, because as I said, for now, they are produced, we assume that the shares of today, but it's going to be a question of future industrial trade and climate policy, how and where these jobs are being created. So to wrap up, we did this kind of exercise to estimate direct energy jobs today, out of which 12 million are basically in fossil fuels. We see some increase in the reference scenario over time, and a bigger increase in the well below 2 degree scenario, with a big potential for these manufacturing renewable goods, which we call a global pool. I think it's very relevant to discuss and know these numbers, and to maybe even include them in further energy modeling exercises, which is why once this kind of exercise is finished, we aim to publish also the data set for further analysis and extensions, maybe during the fall of this year. And with that being said, I'm happy to end my talk and hand over to Zoe for her discussion.
Thanks, Johannes. Very interesting, and let's move straight away with Zoe. Zoe Vrontisi, she's a senior researcher at E3 Modeling, long-standing collaborator. She's done a lot of work on the modeling of the energy transition in Europe and outside Europe, and she has looked at employment quite a lot on the modeling front, quite sophisticated modeling. So Flores is yours, and after Zoe's talk, we're gonna open for Q&A. Thanks.
Thanks, Massimo, and thank you for the invitation and for the interesting discussion and presentation, Johannes. So I'm going to present the main insights from the research work that we have done recently in E3 Modeling regarding exactly the labor implications of the clean energy transition, both related to direct but also to indirect and economy-wide jobs. And we have also looked at the labor intensity of energy-related technologies. And if we look at the power technologies here, we find that on average, the renewables are more labor intensive and have a higher domestic job content than fossils. This is also important for our analysis, also for the analysis of the direct, but also for the overall economic impact of the transition. So when we analyze Europe in particular, we find that most of the renewable technologies, their domestic content is high. Of course, for solar PV, this is not the case for manufacturing, but we find that most of the jobs are generated during the installation and the operation and maintenance process. Coal is also very labor intensive, but this is mainly due to the coal mining process and the fuel supply process. We also see that gas, for example, has a lower labor intensity due to the high automation and the mechanization processes. Wind is another good example where we see that most of the jobs come during the operation and maintenance, but also during the manufacturing, and the entire manufacturing is taking place in the EU. So this is a very important basic element for our overall analysis, as Johannes explained as well. This is a very labor-intensive process for us modelers and researchers to get the data and calculate the labor intensities. And we have also done this for the transport fuels, the transport technologies, given that the decarbonization of the transport sector is key for the clean energy transition. And here we find that the labor intensity of oil is actually the lowest compared to biofuels and electricity. We measure here jobs per kiloton by transport fuel, and we also assess the different phases of the energy service by each transport fuel. So the production, processing, and the sales. Of course, for oil, sales takes up a big share of the jobs generated. But for example, for biofuels, we find that both production but also the processing is very much important. Now, when we measure jobs per activity, per transport activity, so per kilometer, we see that biofuels generate more jobs than oil and electricity. And the content is actually mostly domestic. Now, quickly going, let's say, to the assessment of the direct energy jobs. This is already presented in a paper published by my colleagues Panagiotis Fragos and Leonidas Parousos in 2018. What we did there is that we assessed the European 2030 targets, and in order to understand both the direct but also the indirect labor content of this transition. And on the direct side, we find that the effects are positive both for 2030 and 2050. And this is the case mostly for electricity, also due to the electrification of final energy demand, transportation and heating uses, and also on the biofuel side, which are quite labor intensive. And we see that the jobs lost are mainly in fuel cells and fossil fuels. So this is expected, but let's say the new findings here relate to the overall direct energy jobs that for Europe are positive for a scenario going to 2 degrees. Now, if we want to look at the overall economy-wide effects, in EFI modeling, we do this with the GEMI3 global general equilibrium model, and we need to take into consideration a number of drivers that actually play an important role in estimating these economy-wide effects. Of course, we have the direct energy sector effects, where it's important to understand the domestically produced clean energy technologies versus the conventional energy sector. So, of course, in our regional results, as you will see later, we expect to see fossil fuel exporting regions to have negative effects on an economy-wide, but also on the energy-related jobs. But then we also need to take into consideration the industrial competitiveness effects. And there, these effects are driven by various price effects. For example, the energy cost changes, whether the prices, energy prices, increase or not, and how does this affect the overall production cost, and how does this affect then the competitiveness of the product, and then the trade dynamics of the regions. Economies of scale and technical progress also play a role here. In our model, we have also endogenous technical growth that is related to the emergence of these new clean technologies. And there we expect to see through the spillover mechanisms reductions in prices in the production cost, also in non-energy related sectors, just because all these sectors take some knowledge from the transition progress. But also the regional value chains that play an important role also for the evaluation of the overall industrial competitiveness. So this is one side that affects trade, and trade affects the overall economy, and through that we can see the impacts on jobs. But at the same time, we need to take into consideration the different skill and labor market formulation and the impact that this has on households. So the GEMI3 model features 5 different skill levels for each sectoral activity, and we find that the transition requires new skills, more, let's say, technical skills. So if we think about the transition from the coal mining to the more technician style jobs of the wind park or the solar PV, we also take this into consideration, but also the labor intensity of the growing sectors and the different levels of income and consumption patterns that are related to the new skill demand. Of course, we also take into consideration the energy expenditure that can change the disposable income of the households, and this affects the consumption of different types of goods and products. And last but not least, we have the consideration of the financial implications, where the financing requirements need to be taken into consideration so as to account for the debt and interest payments both by households and firms, and understand the implications of these on the limitations of disposable income and a potential crowding out of investments for other type of goods and products. So let's say the complex system of a general equilibrium model like GEMI3 can cover all of these aspects in order for us to get a grasp of the economy-wide effects of labor implications for the clean energy transition. Now, I will present just very few results from recent research studies that we have done with GEMI3 model. This is a similar scenario like the one presented by Johannes, so it's a global well below 2 degree scenario, and what we did here is we tried to assess, apart from the economy-wide implications that are driven by the implications also of economic growth, we wanted to understand what are the implications of a carbon revenue recycling scheme. We see that the carbon revenues are a large share of GDP in many regions. For example, on an average on the world, on a global level, carbon revenues are almost 4% of global GDP in 2015. So this is a good amount of money, and we see that if we try to direct with the specific policies, try to direct this amount towards the lowering of labor costs through the reduction of social security contributions, we can then see very different effects, both on the macroeconomic level, on a GDP level, but also on employment. So the right graph shows the global employment changes in 2015, and the left column is the scenario with the recycling towards the social security contribution reduction, and the right column is when we recycle this towards the reduction of indirect taxes, so the overall, let's say, taxation of the economy. And we see here, you see with the white dot there, it's the total employment effect on a global level. And we see that effects differ a lot between these two recycling options, and that actually, even on a global level, we can find positive effects for the overall economy. Of course, both scenarios indicate gains on the energy sector when it comes to power generation, transport, biofuels, electric vehicles, and other clean energy technologies. Of course, a reduction of fossil fuel and energy-intensive industry jobs. But we also see that with the direction towards social security contributions, we have an overall positive effect for the global economy. Now, if we look on a regional level, results with
just 1 minute sign, sorry.
Yes, thank you. So on a regional level, we see that the effects differ also a lot. On the left hand, we have the social security contribution recycling scheme. On the right hand, the general taxation, and we see that the columns that indicate the employment impact can actually, the negative employment effects for certain regions like China or India can be mitigated, while other regions can even have positive effects, like Brazil, Europe, Japan, etc. So this is a very brief insight and just a contribution for this very interesting discussion of the work that we are doing with EFRE modeling and the GEM-EFRE modeling. Thank you very much for your attention.
So thanks, Zoe, thanks, Johannes, for both your contribution, which are quite complementary. For the crowd, we have 10 minutes of Q&A, so I encourage you to write your questions if you have any in the chat. I will, cherry pick, try to combine questions. There's a large crowd attending of almost 150 people. That's the advantage of COVID webinars. So I assume there will be questions. There are already some coming in, so let me pull out some of the topics. Wages has been mentioned in some of the chat. Can you say anything about wages? It's not just a question of jobs, it's a question of quality of jobs and payment, of course, and the transition between coal and between dirty and green jobs. There's a question also of the cost of educating and transitioning towards job search and job switch. So if either of you can comment on these questions, meanwhile I'm gonna look through the chat. Both of you will be great, actually.
Yeah, just very quickly, I think, yeah, there are very important topics, quality and wages. So far, we haven't looked into it. We know it's important, and yeah, we're considering ways of doing it. I know Zoe has, at least on the wage part, I think, something to say. But yeah, in my analysis, it was not considered exactly.
Yes, thank you, Johannes. Yeah, indeed, this is, let's say, the next type of analysis that we are undertaking now in EFRE modeling. And with regards to wages, we find that understanding the different skill requirements is key here. Because, of course, different skills are related to different types of wages and income levels. And so we find that so far our findings is that the clean energy transition is related to for demand for higher skills, which can indicate higher wages. Of course, in a general equilibrium framework, it's also important to understand the overall macroeconomic impacts. So if we have, let's say, a lower domestic production, this can also reduce wages. But so far, our understanding is that skills play a very important role there.
Yes, absolutely. And there was a question about what extent the models can grasp the impact on skilled and unskilled labor. One question was about the extraction of minerals that you need also for renewables. For example, solar PV needs a certain numbers of extractions, for which, of course, there will be a demand in the extraction sector, which could be used or partly compensate or be collocated, as a matter of fact, in those regions that experience the largest losses. Has either of you looked into this or thought about it? All the value chain, essentially.
Yeah, go ahead. Sorry, maybe.
Okay. Yes. So we have not yet integrated this type of, let's say, rare earth materials in our modeling, but we are now considering of doing that. We are now in the process of analyzing also the implications of the megatrends, of some megatrends with the clean energy transition. And of course, this is an important issue where we see that some trade conflicts can emerge exactly due to the rare earths that are related with the production of some clean technologies. It is quite difficult to integrate this in an economic model, merely because of the lack of availability of data in economic units. It's easier to do this in physical units. So we are considering now, we're in the process of considering how to do this.
Thanks. An important question, the race between jobs and technology, that's always a classic. And so we have a question from Tim asking, have you looked into the potential for automating jobs between different sectors? Is there any data that keeps tracks of to what extent technical change over time has changed intensity, jobs intensity in sectors, in different sectors, especially for the growing ones such as renewables?
Yeah. Shall I give a quick response? Yes. We recently did an analysis on this through this megatrend assessment on the higher automation of the economy, and we hope to publish something soon on this. And our findings is that, of course, we expect to see, let's say, a job shift from certain sectors towards other sectors. And this is just because this higher automation brings an overall higher technical growth in the entire economy and has indirect and induced positive effects. So some sectors may lose jobs, but we can see other sectors and new jobs being generated just because of this technological growth process.
Yeah, it can be an important factor. We also looked into this, but there's very little data historically. Plus, some are very mature already, and some of the new jobs like renewables are quite advanced already technologically. So but empirically it's hard to look at it at this point.
There are questions about more technical questions about, for example, you see a lot of, for Johannes, projections twice as much PV manufacturing jobs compared to jobs in construction and operation and maintenance. But of course, for PV, it matters whether it's rooftop or utility scale PV, and the job intensity between the two will change. And of course, the relation between the two, at what extent one will dominate the other in future scenarios, depends on scenarios and models. Have you looked into this differentiation?
Yeah, that's a good point. Of course, these technologies are not all the same, and this holds for several of these. We did it at, for instance, at hydro. Also, there's a difference between big hydro dams and small scale pump storage. Same also for oil. I mean, there's difference between conventional. So there's a lot of detail. we always try to take the best data that was available. They're available taking, let's say, weighted averages, but of course this is as of today's level. So indeed, if let's say there were a big shift in some technologies, we might see some changes. So yes, so we looked into it, but we didn't model them differently. So
okay. And then of course, as a last question to both of you, of course, the inevitable question is about what's happening now and what extent the crisis will affect jobs in the future. If you've done any thought or modeling about this, and what's your view? There were several questions regarding this, of course. Seems we cannot not talk about it.
Yes.
Oi?
Yeah, it's a big issue, and yeah, most of the researchers have been asked about this these days. And our initial take, we did some very preliminary runs on the COVID situation, and what we find is that there is scope to if there is scope for, let's say, a faster transition. If some policies are considered, but with regards to the labor implications, yeah, this totally depends on the assumptions on future, well, whether the economy will recover sharply or not, and we only did some sensitivity runs for this. So it's not, a one-off response to that.
Of course. Johannes, final word?
yeah, I agree. It's interesting, important, of course, topic of the hour. When it comes to energy jobs, I mean, also we had this oil price crash earlier this year, which was related, but of course very different, which had its own implications, of course, on the whole sector. So I think to disentangle all these effects is challenging, to say the least. Now, in general, the jobs that we consider are kind of permanent jobs that are persistent over time. So that's how we define the jobs. There's different job years. Of course, there can be an impact. It would be interesting to look at, and it may be with some more time passing, and we see how it has been changing the system. But yeah, still probably not the biggest impact on energy system jobs for now.
All right. And the entirety of energy system jobs, after all, the 70 million number you put, have to be put in the global context of global employment numbers. So thanks to all the speakers. We just had the hour. Thanks to everyone who has attended the conference. Just to remind you that some of the material that Zoe presented, I believe, is published or are public documents. Is that correct? Yeah. The paper that Johannes presented is currently submitted, so it's not available, but hopefully it will be available soon, along with the underlying database. The registration of today's talk will actually be public on the YouTube channel of our institute, so you can find it there. And thanks again for listening, and I guess I'll see you at the next webinar. Might be on something related to COVID, as just discussed. Thanks to the speaker, great talk by Zoe and Johannes, and see you all very soon. And of course, stay healthy and safe.